Good morning. So here we are back looking at chapter 33. We're looking at lenses, and we had finished up on our last lecture looking at cameras and how cameras operate in terms of where is the object, where is the image, where is the placement of the lens. And now we're going to look at kind of a related topic, really, the human eye, or, you know, a lot of different organisms have eyes. But if we think in terms of the human eye and corrective lenses, here's a diagram of the eye. And so let's start with this. So most of the eye is actually not visible, right? When you look at someone and you're looking at their eyes, you're really only seeing this portion at the front. You're really just seeing this cornea along the front of the eye. Most of the eye is hidden back behind that. So you really don't see it. So there are these, you know, this spherical kind of eye back behind there. And then in terms of kind of the basic ideas here, we're going to have objects and light coming off of objects. We want that to be in focus on a screen. And the screen inside the eye is called the retina. The retina consists of like 3 distinct layers of different types of neurons. So at the back layer, the farthest back layer, are the photoreceptors. Now this is kind of interesting because in some ways the architecture is kind of backwards from what you would think. But there is a layer of photoreceptor cells, cones and rods, at the back layer of the retina. And that's actually what is sensitive to the light. So in order for the light to reach the retina, the light's coming through the lens at this location, in order for the light to reach that location, it actually has to pass through some other layers of neurons until it reaches the photoreceptors. But it works, apparently, right? So those thin layers of neurons are really thin, and they don't have much of an effect, and the light processing scheme still works. So the farthest back to the photoreceptors, those are the rods and the cones that you're probably familiar with from your other science classes. The rods are able to distinguish kind of black and white and shades of gray. The cones are sensitive, are distinctly sensitive to different parts of the visible spectrum. So there are cones that specialize in, are sensitive to the red part of the spectrum, cones that are sensitive to the green, cones that are sensitive to the blue. And when you think about it, how many colors are you able to see? And you're able to, I mean, go to a paint store, right? And look at all the colors that they have, the thousands and thousands of possible colors that they can mix. So by changing the amount of red, green, and blue activation, depending on how much we activate the red sensitive cones, the green sensitive cones, and the blue sensitive cones, the processing in our brains are able to turn that into the experience of, you know, all the many thousands or tens of thousands of colors that we observe. Kind of remarkable, right? Next time you're watching a really beautiful sunset, think, oh, this is all being done with my red, green, and blue cones, right? 3 different visually sensitive materials. And it's kind of an interesting quantum mechanics question too, because the way that works is these cones have proteins embedded in the cones they're photosensitive, and those proteins have little rhodops and molecules in them. And when a photon, when a particle of light is absorbed in the right energy range, when that gets absorbed, the molecule changes configuration. So especially if you guys have taken like organic chemistry and talked about configurations of different molecules, how they bend back and forth, organic molecules. Boy, that's what happens. And then the protein shifts, and that shift ends up generating a signal along the neuron. Now the neurons, so let's get back to these layers here. So there's this back layer of cones and rods that are photosensitive. Then there's a middle layer of processing cells. So it's not like pixels. It's not like one cone or one rod sends one signal. What happens instead is there's an intermediate layer of cells that are kind of the first stage of photoprocessing. And so what they do is they take signals from many different photoreceptors and decide whether or not to pass on a signal based on that pattern. So there's already signal processing taking place. And then finally, the innermost layer, called the ganglion layer, are the ones that pick up those signals from the processing cells, from the intermediate layer. And those signals then get sent along the optic nerve back to the brain. So that optic nerve goes back to the brain. Now, you guys from your biology classes probably know that some neurons, neurons pick up signals from their dendrites or whatever, and then they pass this along an axon, and some of these axons are really long, right? And the eye, the human eye is an example of that. These ganglion cells, whose cell bodies line up along here, their axons actually make up the optic nerve. So those cells on that inner layer of the eye actually have these long axons that extend outwards, and they go all the way into the brain. So these cells actually have those axons that are extended all the way back into the brain, where the first stages of processing, optical processing, are done in the brain. So in some sense, the retina is kind of an extension of your brain. These cells have migrated from the brain area during development, and they make their way out and plant themselves out here, those few layers of processing, plant themselves at the back of the eye. So there's a little bit of brain at the back of your eyes processing that information. So anyway, just one of those remarkable things that we run into. Now, for our purposes for this chapter, we're mostly interested in this. There's going to be a bunch of objects out here. Light from those objects is going to be spreading out in different directions. What the eye is going to do is take a sample of that light, converge it, bring it together, and form an image. Now, we've seen that with lenses. That's what converging lenses do. Now, in the eye, there's kind of two stages of convergence that takes place. There is this front surface, the cornea. Now, outside of the cornea typically is air. So what we have is a boundary between air on one side and cornea, or the eye, on the other side. The index of refraction here is like 1. Index of refraction here is more like water, like 1.33. That is a single refractive surface. Back from chapter 32, if you remember, maybe the last topic we looked at in chapter 32. So that's a single refractive surface, and the cornea, that curvature on the cornea, is where most of the convergence takes place. So it's easy to think, oh, it's the lens that's creating the curvature, the converging effect and creating the image. But the cornea all by itself is already bringing that light together. Now the lens fine-tunes that. So the cornea does most of the converging, and then the lens creates a little more convergence if it's needed, a lot more convergence if it's needed, and that's what allows us to focus on objects that are far away or close in. If we're looking out in the distance, if we are looking way out in the distance, then we don't really need very much convergence from the lens. But if we're looking at something close, we need a lot more convergence. So what happens is these surrounding ciliary muscles are relaxed when we're looking at distance, and when we're looking at something close up, they're contracted. And when these muscles, now that's a ring, a circular ring of muscles, when that circular ring of muscles contracts, the lens bulges, the lens spreads out a little bit, and that creates more convergence. So that's a pretty cool mechanism. Back when we looked at the camera, we said, well, how do we adjust for objects close and objects far away? And when it was a camera, what we did was, for the camera, what we did was we had the lens move back and forth. Well, in the camera's case, the lens had a fixed focal length. But in the case of the eye, it's the lens that's flexible. So we don't need the lens to move back and forth. We just have the lens change its focal properties by contracting those muscles. All right, where is the image for all this? Well, the image needs to be at that layer of photoreceptor cells. So to get the sharpest image possible, we want an image to be placed at the location of the photoreceptor layer. If it's not there, then the image is blurry. If it's not even close to being there, then the image is really, really blurry. And that's where corrective lenses come in. If a person's eye is unable to provide what we consider to be, standard kind of vision, then we use corrective lenses to bring it back into compliance, or back so that that person has standard sorts of visual ability. Okay, so let's see. If we drew a diagram on this, then we would have a central axis here. I'm going to start with the fovea. The fovea is the center of the retina. That's where the cones are as densely placed as possible. That's where we have our best color vision. Our most acute vision is in the fovea in terms of color vision. That's the best, highest quality vision that we have. So if we start with there and then draw our dashed line out, there's going to be an object out here somewhere, right? And then we're going to draw lines through here, and those lines are going to follow different paths of light back to where the retina is located. Okay, and we want the lines to converge so that they're giving us a sharp image. Now, very quickly, I guess, when I was a kid, I had to have corrective lenses. I actually needed the corrective lenses like when I was in the second grade. By the time I was in the second grade, I needed corrective lenses. But I actually didn't get them until I was in fourth grade. And that happened because when we would get our vision tests each year or each semester in elementary school, they would line all the kids up and have them take the test one at a time. And I would always position myself at the back of the line, because you could actually look at the eye chart, and by the time it became my turn, I kind of had the letters memorized. So everything was just a blur, but I could see where the person was pointing, and I could still... Anyway, I cheated on my eye exam for a couple of years until they finally, in class one day, my teacher asked me to read something from the board, and it was just all a blur. So anyway, corrective lenses for a long time. A few years back, I ended up having cataract surgery. So my lens had become cloudy, and you've probably heard of cataract surgery. So what they're able to do is take out the lens and put in an artificial lens, and they're actually now really good at this. I mean, my cataract surgery has been, actually now it's been about 20 years ago. So I had cataract surgery 20 years ago, and they put artificial lenses in both eyes, left and right. And, these artificial lenses that did away with the cloudiness of the lenses, my original physiological lenses that I had. So I now have artificial lenses in here. Now, the artificial lenses are not flexible. So they're not able to respond to those ciliary muscles. And that says that I just have one fixed focal length. The focal length's not changing. Now, when the doctor said, what would you like to have for your focal distance? I chose distance because, as a kid growing up and kind of my whole life, I'd always had to wear glasses for distance vision, and this was my chance to have my distance vision back. And so I said, hey, 100%, I want distance vision, I want my distance vision back. They were able to do some measurements, sent some lasers in there, did some measurements of my eye, and it worked. You know, they put the artificial lenses in, and for distance vision, my vision was 20/20. It's drifted a bit in the past 20 years, but it's still pretty close to 20/20 in each eye. So that's the good news, right? The downside of this is with my new lenses, I no longer can focus on objects that are close. So, you know, I knew that going in, and so I just figured, you know, I'm going to get some of these reading glasses. You can go to the, you know, the drugstore and get a pair of reading glasses for $5. And I just leave reading glasses. They're kind of on every counter at my house. There's always a reading, you know, some reading glasses there, and I pick them up and put them on if I need to look at something close and focus on that. So anyway, that's kind of an interesting example, a physics example from what we're looking at. If I replace this variable lens with something that is fixed, then I go back to this idea of I'm going to need some corrective lenses for close work. Now my doctor at the time said, what he kind of suggested doing, he said, you know, most people choose to have one eye corrected for distance and one eye corrected for close work. And I said, you've got to be kidding. Isn't that super confusing for your brain? He said, no, he says it takes a little getting used to, but within a few months, most patients don't notice it. So when they're looking distance, they're really just taking in visual information from one eye. Their brain's just using that eye. And then when they're doing close work, it just switches over. So the brain's just using information from the other eye. But, you know, I wanted my full 180-degree distance vision in place. So I said, no, I'm going to go with the reading glasses version where I just have to, you know, carry around some corrective lenses for close work. All right. Lots of discussion on this. A lot of applications to kind of like our everyday life. Really interesting kind of examples here. I'm going to move on. Not stay on this one forever. Here we go. So let's correct some vision. So the idea with vision is, well, we talked about this. If an object is way, way far away, then the light is coming in almost parallel, and I'm getting a lot of convergence at the cornea, and then the lens is giving me additional convergence, and it's coming to a focus here. Well, what happens now if I want to look at an object that's nearby? Well, I tighten those ciliary muscles. This is all involuntary, right? It just happens automatically. So infants, when they're learning to see, are practicing contracting their ciliary muscles, I guess. And so here's the object nearby. I need more convergence for this. And so what happens is you tighten those muscles, the lens bulges. See how the lens now is bulged? And if I think back to how converging lenses work, with those smaller radiuses of curvature, I'm going to have a higher converging lens, a more powerful lens. And so that's how it works. Okay, so human vision works along those lines. Now let's do some, set some standards. So we have what's called a near point. The near point for an individual, for actually one of their eyes, is the closest distance at which that eye can focus clearly. So normally, if we go back to this picture before, to be considered to have normal vision, you are supposed to be able to have an object 25 centimeters, you know, about that distance from your eye, and you're supposed to be able to focus on it. So you should be able to focus on something this close. Now I can't do that with my lenses, my current set of lenses. But at 25 centimeters, you're supposed to have enough converging ability in your eye to give you a sharp image. If you can focus on things closer than 25, great, you know, that works. But 25 is considered normal. Now the far point is infinity. So, and again, going back to this picture from before, so let's say this is, you know, this is designating the person's far point. Yes, they can focus when light is coming in from an object at infinity. And then this is the near point. Yes, the person can focus on something placed 25 centimeters from their eye. And then they can focus on anything in between. So there's like this near point and this far point. And the near point for normal vision should be 25 centimeters, and the far point should be infinity. You should be able to focus all the way out to infinity. Now what that means, you go, wait, I can't see things that are infinitely far away. It doesn't say you necessarily can see them. It says that anything that's placed infinitely far away should still be in focus, no matter how far, as that thing gets farther and farther away and it's getting harder and harder to see because it's getting small, it should still be in focus. What's the most distant object you can focus on? And I'm going to say maybe it's the Andromeda Galaxy. The Andromeda Galaxy is really big, but it's, it's like millions of light years away, and the idea with this is, when you look at the Andromeda Galaxy, it should be in focus because, it's a very distant object. So anyway, that's the idea with this. So let's see how we can correct. Here's a person. They're coming in. This is called, our patient here is nearsighted. What nearsighted says is this. It says the person's doing fine with things that are nearby, but when you get out to distances, at some point the person just can't focus on them anymore. The far point is not at infinity. The far point is significantly closer. So here's the person. Here's light coming in from, the person's looking out at something that's distant, far away, and the light is being overly converged. So for this person, the lens is too converging, or the shape of the eye is too elongated, and what that's going to do is mean that the focus is not going to land at the retina. So what we do for that is we put in a diverging lens. A diverging lens is going to bend the light out a little bit, and then the overly converging system we have here can bring the light back to a sharp focus. So that's what we do. For people with nearsightedness, we're going to prescribe them with some kind of diverging lens, and we'll see how to get the actual numbers on that, how many diopters we want for that. Okay, now the opposite concern is this. What if the person can't focus on objects that are nearby? So in this case, the lensing system is not converging enough. Now, if we go back here, if we go back to nearsightedness, nearsightedness most commonly shows up in younger people. And actually, younger people who are going to school, and they are focusing, they're spending a lot of their time looking at things that are really close to them. In any case, this tends to create, in a lot of situations, this nearsighted effect. Whereas with farsightedness, where does farsightedness typically show up? And most commonly, farsightedness shows up in people my age. As you get older, the lensing system becomes less and less flexible. And mine's not flexible at all because it's an artificial lens, but typically, as a person gets older, their variable lens gets less and less flexible, and that means that even when you're trying to tighten it and have it bulge out, it just doesn't bulge out as much. So you lose some of that converging effect in that lens. Now, what we can do to correct for that is we can give the person some glasses, give them some corrective lenses, which are a little bit converging. So that creates a little additional convergence. So the lens is no longer able to come up with all the convergence it needs, but we'll correct that with a converging lens. And again, we'll look at examples for both of these, nearsightedness and farsightedness, and see what the specific prescription should be. Any of you going into optometry? So here we go. Here's an example. Human eye, corrective lenses. We're going to start off with somebody who's farsighted. Now, this is Sue, and Sue is farsighted and has a near point of 100 centimeters. So what that's saying, and that's probably about where my vision is. So this person, anything closer than about a meter out, now that's arm's length, the person cannot focus. So, in the store you see these people standing back away from the shelves trying to read the read the product labels from like a meter away, because if you get closer, it's just kind of blurry. So we want to give this person some corrective lenses. We want to put some corrective lenses in place that allow the person to hold something at the standard 25 centimeters. So we want this person to be able to hold something at a standard 25 centimeters and focus on it. So what that says is this. It says, I want a lens where I can place an object with a DO of 25 centimeters. And I want that lens to create a virtual image. And I want the image to be virtual because I want it right side up. I don't want to put on corrective lenses and have everything go upside down. That would take a lot of getting used to. So anyway, I want a DO of 25 centimeters. I want a DI of, well, for this person, I want a DI of 100 centimeters. And I want the DI to be 100 centimeters because, hey, that's where Sue's near point is. As long as the image is out here somewhere, our patient is going to be able to focus on that light. So those are the numbers. This is the lens. What we want to do now is we want to calculate what the focal length should be. All right, here is the setup. Again, here is the eye right here. If I place the object at 25, this person's eye can't focus on it. But if I place a lens here, which is this line running vertically, oh, there it is, lens, in such a way to generate an image out at 100 centimeters, the person's going to be fine. So let's put the numbers in. DO is plus 25. That's a real object. Now notice the image is virtual. The image is not real. The image is virtual. And that means we have to make sure we get a negative sign in there. If you miss the minus sign, first you might think, oh, if I get the sign backwards, if I miss a sign, I'll get the sign backwards. That's not true. If you take a look at this formula, it's more complicated than that. What I'm doing is I'm taking 1 over 25 plus 1 over 100. If I switch just the sign here, it's going to give me something completely different for the focal length. So it's not like just, oh, I have to flip the sign. It's like I'm going to get a different number also. But that minus sign is crucial for these corrective lenses. So 1 over 25, 1 over minus 100. I put the numbers into the formula. I calculated 33.3 centimeters. So that's the focal length of the corrective lens that I want to use. Okay, that seems fine. Now to put that into diopters, right? When you go to the doctor, or the optometrist, the ophthalmologist, and they do a prescription for your eyes, they report that in diopters. So we talked about that being the power of the lens. So what I'm going to do is I'm going to take this 33.3 centimeters that I calculated, I'm going to put that into meters. So I'm going to convert that into meters, and then I'm going to take its inverse, and that will give me an answer in diopters. It turns out that it's plus 3 diopters. So that's it. That's the prescription we're going to have for this person. We're going to prescribe them with plus 3 diopters. They're going to put these lenses on, and now the light that's coming into their eyes is already pre-converged by that lens, and then their own eyes are going to have enough converging ability that they can bring that light into sharp focus on their retina, and they're going to be able to see, is what we call it. When we say something is in focus, a lot of times we say, oh, now I can see, when in reality we should be saying, oh, now it's in focus. Okay, we could see it before, but it was all a blur. All right. Here's another corrective lens example. Here is our nearsighted example, 3313. So I relate to the example we saw above. When I first came out of cataract surgery and got my eyes back, so I was used to my new lenses, that's about what I was at, was about 3 diopters. And anyway, that's a pretty typical number. Let's see. This person is nearsighted, and it says that this nearsighted patient has this is interesting, they have a near point of 12 centimeters and a far point of 17. Now you might think that's extreme, but it's not really so extreme. That's fairly common. You know, when I was a kid, by the time I was in middle school, probably, those were probably typical numbers, not about what I had. So that says that my eyes are overly converging. And they're so overly converging that I can only focus out to about 17 centimeters. But on the other hand, I can focus as close as 12. So there's this very narrow range where I can actually have things in focus. So I have to, hold something here to be in focus and forget about trying to see anything far away from me. So let's see what we can do for this person. What we're going to do now is, we said we were going to use a diverging lens, so that's what we're anticipating we're going to end up with here. Now this time, we didn't do this in the last example, but it's very common in these examples to allow for a couple of centimeters between the eye and the corrective lens. So that's typically what we want to do. Now you could also be doing this with contact lenses, and if you did contact lenses, then you forget about the 2 centimeters. But for our purposes in this example, we're going to say these are glasses, here is the lens, it's 2 centimeters from where the eye is located. So what it's saying now is I want to be able to take an object that's at infinity. So my DO, this time, is going to be infinite. DO will be equal to infinity. And then where do I want the image from this lens to be so that my eye can focus on it? And the farthest out it can be is 17 centimeters, because that's what they've told us about this patient. So I'm going to take 17 centimeters. Now this is not from the lens, this is from the person's eye out to where the image is located. So that says I have to make this 2 centimeter adjustment. I actually want the DI. The DI is going to be 15 centimeters. Okay, and so that's part A of the problem. Now part B on the problem says this: when the person is wearing these corrective lenses, what we know is that the person's far point is now going to be infinitely far away. They can focus on things far away. What's it going to do to the person's near point? That is also going to be affected. So it's not just the 17 centimeters that's going to get replaced with infinity. The 12 centimeters is also going to get larger. So the person is not going to be able to hold something like right here and read it. They're going to have to hold, they've gotten used to holding materials close to their eyes to read it. They're going to have to hold it out a little bit more. They're not going to be able to see as much detail, right? Being nearsighted actually enables a person to focus on something closer, typically, and to see more detail. All right, let's see how this looks set up in our formulas and our diagram. So this is what my diagram, this is what the formulas look like. This is what you working on homework problems is going to look like this. Exam problems are going to look like this. So I'm going to start with this. Near point 12 centimeters, far point 17 centimeters. Here is the person's eye. We're going to do one chart for the far point, and then we'll do another diagram for the near point. Now for the far point, we're saying I want the object to be infinitely far away, and I need a DI that's right in here. So as we talked about from the page before, the DI needs to be 15 centimeters. Now, I've got to remember that minus sign again. It's a virtual image, and that means that I've got to get that minus sign in there, or I'm going to get a crazy answer. So I did that. I put all the numbers in. The 1 over infinity is easy enough. That just becomes 0, right? You're thinking, where's the infinity button on my calculator? But 1 over infinity is just 0. We can just ignore this term. And the focal length then just becomes DI. The focal length is negative 15 centimeters. Now that's a diverging lens because it has a negative focal length. To find the power of that, I convert this to meters, and then I take the inverse, and it turned out to be minus 6.67 diopters. Now that's a little beyond what, I think my prescription at one point was probably minus 5 diopters, something like this, but 6.7 doesn't sound so extreme. And so that's what the power of the lens is. This is what the focal length is. All right, so we're going to get that person prescribed. We're going to get those lenses made up and a pair of glasses, and this person's going to be able to see distance really great. Part B on the problem is asking then, okay, when the person's wearing their glasses, now they can always take their glasses off and then bring that stuff into 12 centimeters away. But if they're wearing their glasses, how close can an object be now and still have that be in focus? So we're going to solve the problem this way. We're going to say, oh, this time it's the DO that I'm solving for. I'm trying to find out where I can place an object such that it's going to be in focus. Now, the image can be as close as 12 centimeters from my eye, because or this patient's eye, because that's the properties of this patient's vision. So this is 12 centimeters. I got to subtract off that 2 centimeters because of the placement of the lens. And that says DI needs to be 10 centimeters. More specifically, it needs to be negative 10 centimeters. So I'm going to say DI is negative 10 centimeters because it's a virtual image. And when I go through and solve the same formula, but I'm rearranging it to solve for DO, DO says 30 centimeters. So when this person's wearing their corrective lenses, they are going to have to hold objects at least 30 centimeters away in order to focus on it. Okay. So again, if you're kind of like, I mean, many of you probably who wear corrective lenses already do this, but you know, growing up all through school, elementary, junior high school, college, I just took my glasses off if I wanted to go back to reading things close up. But anyway, this person is going to have, their new near point is going to be 30. Their new far point is going to be infinity. Okay. All right. So take a look at these. These are problems, very useful problems to think about. One of the best inventions ever. Anybody who wears corrective lenses understands, gosh, getting your vision back is that's just remarkable. Getting it back to where you can see things in focus. All right, we're going to move on and take a look at this example. This is just a talk about problem. What it says is that when we go underwater, this is kind of interesting. When you're swimming and you dive under the water and you open your eyes, everything's blurry. Now, my vision was working fine up in the air. Why is it blurry now that I'm down under the water? And remember what we talked about a few slides back is that most of the convergence that brings together the light and creates an image for us is done at the cornea, and it depends on the indexes of refraction on either side. So in order for a person's vision to work, they need air. They need something with an index of refraction of 1.00. The eye naturally is adapted so that the outside index of refraction is 1.00. Well, now what we've done by diving under the water and opening our eyes and looking through the water, we don't have that difference anymore. Now what we have is 1.33 on one side and actually something very close to 1.33 on the other. Turns out that most biological material we can treat as being water, and in terms of specific heat capacities and things like that. Well, also in terms of optical properties, we can treat these physiological tissue as having an index somewhere around 1.33. So what we've done then, if this is 1.33 and this is 1.33, we've lost all the convergence of that surface. The light is just going to go straight through. We're not going to get any of the convergence, and that's an extreme effect. And you guys have seen this from diving underwater and opening your eyes. Now, what's remarkable is that if you wear goggles, the vision becomes sharp. How is that possible? That seems kind of miraculous. Is it like corrective lenses? And it's not like corrective lenses. What it's doing, what the goggles are doing, is they're reestablishing an air cornea boundary. So now at the cornea we have the n equals index of refraction 1.00 outside the cornea, And now we're getting the converging effect of the cornea restored. So now we can focus. Now, how do we deal with this boundary? Because the light's got to come out of the water and go into the air. And for that, we use an effectively almost flat surface. If we use a flat surface for the front of the goggles, we don't want it to be highly curved. If we use just a flat surface, then the light that's coming in won't refract one way or the other. Okay? So it will be able to pass through the goggle without being affected. It's not going to bend because of the presence of the goggle. So the light here goes straight in. I don't know if they've drawn their diagram to show that. I think they've got it wrong a little bit. Anyway, so the light's coming in through that goggle, and now it's just back to the normal setup for vision with air in front of the cornea. So good to know, right? How those goggles are operating. Okay. All right, we spent a fair amount of time taking a look at human vision and some of the corrective lenses. I think it's a really interesting and very applicable part of the chapter. So make sure that you take a look at these examples, take a look at the homework problems related with corrective vision. Something to spend some time thinking about. All right, we are going to move on to another really important topic in the chapter. This chapter just goes on and on, right? So there's a lot of stuff built into chapter 33, and that's why we have a couple extra, we'll have a total of 4 lectures on this. And so we're now going to look at, well, they're calling this magnifying glass, but what this really is looking at is a concept called angular magnification. Now, the magnification we looked at before was lateral magnification. Now we're going to look at angular magnification, and we'll take a look at their diagram here. I've got one that follows that shows a little more detail, but their artist is pretty good here, so let's make use of this. So the idea with a magnifier is that we're going to take a converging lens. We're going to use that converging lens to take light from an object. We're going to place that object inside the focal point, and that's going to give us a virtual image, and that virtual image is going to be much farther away from the lens, and it's going to be much bigger. Now, in terms of lateral magnification, this image is much, much bigger than this object. But in terms of angular magnification, if I take an object and I create an image that's 10 times bigger, but I place that image 10 times as far away, am I going to be able to see more detail in it? And then you go, no, you haven't had any boost in seeing any detail, because, making the image 10 times bigger than the object, that was a great idea. But if this lens places it 10 times as far away, it's still going to have the same angular size to it. So if I take a look, here is the angular size of this object. So if we draw that axis through the lens, and then we take the path of light that runs, right through the lens, through the top of the object, through the top of the image, what we can see is that the angular size of the object and the angular size of the image, they're the same thing. So in terms of seeing more detail, this isn't necessarily going to help, and yet it does, and here's the reason why. What a magnifier enables us to do is place an object much closer to our eye than we normally would be able to do, because it would go out of focus. Remember the near point. If I have normal vision and I can bring an object to 25 centimeters, so here is, I'm trying to look for some object here. Okay, I'll use my keys. So here's an object, and I'm trying to see the detail in this. And I can bring it to 25 centimeters. Now if I keep bringing it in, it gets bigger and bigger in my field of view. The angular size is getting bigger. But what's also happening? it's getting blurry. So my converging power of my, of my lensing system of my eye is not going to be able to focus well on something this close, and it just turns into a blur. What a magnifier allows us to do is this. It enables us to take an object, and using the lens, we can create an image that's, 10 times bigger. Now what we can do, though, is we can take this object and we can place it much closer. So, without the lens in place, DO needs to be 25 centimeters, but with the lens in place, DI needs to be 25 centimeters. So what I can do with the magnifier, I put the magnifier here, and now I can bring the object like here. Now there's a magnifier, there's a lens right here, so the light I'm seeing actually corresponds to an image, and that image is far enough away from my eye that my eye can focus on it. Okay, that's the trick. That's how magnifiers work. And this is a good diagram for seeing all that because, we got to go in now and pay attention to angular size. It's not, in terms of seeing detail of something, it's not how big the image is. It's not the lateral magnification. It's how large can I get the angular size of that image. All right, so, and I'm going to call this angular magnification. I'm going to say this is the name of the topic, is what is angular magnification and how can we design instruments that boost angular magnification. And the instruments here, the optical instruments, include magnifiers, they include microscopes, and they include telescopes. And you go, oh yeah, that's how a microscope works, right? We want to see a lot of detail, and so we're going to use these optical devices, or telescope, we're going to use these optical devices to make the angular size much larger. So angular magnification, we're going to use a capital M, and we're going to define that as theta image over theta reference. Now theta reference is the angular size of that object if I'm not using a lens. What's the best I can do if I'm not using a lens? Now, for our purposes with the magnifier, we're going to use the near point. So here's my near point. Here is my reference angle. I've got an object. It has a size, a lateral size of object height. And if it's object height in size, and it's this far away from me, n, then I can calculate an angle approximately as HO over n. Now that's one of our small angle approximations. It says that if HO is much smaller than n, which it is, HO is much smaller than n, then to a very good approximation we can treat this as an arc distance. Okay, so I'm hoping you've seen this concept used in your other physics classes, Physics 4A, maybe some. Yeah, we used it in Physics 4A and also in Physics 4B. Well, it's coming back to haunt us, and so if that doesn't make sense immediately, you need to spend some time making sure that you understand how that formula is working. Okay, so that's our reference size. That's the best we can do if we don't use a lens. What's the best we can do if we do use the lens? Now, if we do use the lens, then I'm going to define this as an image distance and this as the image height. And so that's, if we go back and look at the picture from before, the angular size of this image, so what we've got here would actually be theta I. So what we're looking at here is theta I. We're using a lens and we're thinking of the angular size of the image in particular. Okay. All right, let's do the math. And so following the formula here, what we're going to do is we're going to take theta I and put it on top. Now, theta I is given by hi over, now I put this as the absolute value of di, and that's because I don't want to confuse myself with negative values. I know that di is negative. Di in this problem is negative, and I don't know how you guys are, but if I can eliminate as many minus signs up front as possible, I do better. I'll lose track of minus signs. And so I'm going to do this right now. I'm going to write this as an absolute value of di. And then I'm going to set that equal to HO over DO. Now HO and DO, they're both positive numbers. So I'm going to get a positive number for theta I by doing this. So instead of writing in the image numbers, I'm going to write in the object numbers because we have similar triangles. Look at that diagram from the page before. And this is going to work. Now on the other side, what I'm going to use is my reference angle. What's the best I can do without the lens? And that comes from right here, HO over N. And so that's going to go in my denominator. Okay, so I'm just following the rules I set up. Now look, the HOs cancel. So the HOs are going to cancel, and then I have to take denominators of denominators, which flips over the values. That says my magnification, my angular magnification is going to be N over DO. So it's going to depend on 25 centimeters. Let's say this person has normal vision and that their near point is 25 centimeters. Well, then my formula for how much magnification am I going to get with this lens is to take that 25 centimeters and, I think I lost track, I'm still here. Take that 25 centimeters and divide through by the object distance. Now, I can't just put any number in for the object distance because the object placement has to give me, there's one more constraint I have to follow. And the constraint here is that the image distance, the absolute value, the positive value of the image distance, the image can be anywhere between my near point and infinity. So if the image is at infinity, then my eye is relaxed. And if you've done any work with microscopes or telescopes or whatever, a lot of times you're told to try, you have to consciously tell yourself, I'm not going to try and use the converging power of my eye. I'm going to let my eye just relax so that I'm not tensing those ciliary muscles all the time. I'm going to let my eye relax and let the microscope do the magnifying. And so that would be placing an image at infinity. But it could, if I did decide to use the converging abilities of my eye to give it a little extra boost, the image could come as close as 25 centimeters. So, so let's solve for both of those possibilities. If my eye is relaxed, and I've got my magnifying lens right up against my eye, and I'm looking at something, that's the intended way that we're going to use this. What happens in the case where my image is at infinity, this term drops out, DO becomes focal length. So this DO becomes focal length, and for a relaxed eye, the magnification of my magnifier is going to be given by the near point divided by the focal length. So I've got to get something with a focal length really small. If I can get a focal length of just a few centimeters, then this is going to give me significant magnification. If the focal length is like 25 centimeters or something, it's not going to help. Okay, so in that case, it's not really going to give me so much of a boost. All right, the other possibility is that I use my eye and I place the image right at my near point. Well, if I use this same formula, what I can do then is go through and solve for the di this time, and it becomes 1 over f. Let's say 1 over d is actually what we're solving for here. That becomes 1 over f plus 1 over n. And so if I solve this one, look, the magnification is larger by 1. So if I relax my eye and I'm using my magnifier, I'm going to get a magnification of n over f, where f's the focal length of the lens. If I'm an overachiever and I'm trying to use the converging power of my lens inside my eye, I'm going to get n over f plus 1. Okay, and those become our range of angular magnification formulas. Okay. All right, this is probably a good place to take a break, so I'm going to stop here, and then we'll come back.